So this video is explaining a process called action potentials, which looks at how we move electrical signals within a nerve cell, also called the neuron. So it's moving a signal within a neuron as opposed to other processes that let us move signals from one nerve cell to the next. So the first thing we need to talk about is something called resting potential. Most neurons, when they are not firing a signal, are at resting potential, and this corresponds to negative 65 millivolts. And the voltage here is comparing concentration of ions, namely sodium and potassium. When we talk about resting potential, we have a concentration of potassium inside the cell, and we have a buildup of sodium outside the cell. So on our diagram here, we have sodium on the outside, we have potassium on the inside. You'll know that both of these are positive charges. So whenever we talk about voltage, we're comparing the outside to the inside. So here, if it's negative 65 millivolts, that means that there is a bigger concentration of ions inside the cell, so the outside is negative by comparison. Also in this diagram we have a few other things. We have what's called a sodium-potassium pump right here. That's the orange. It's not going to be important for a few minutes. The purple is going to represent sodium throughout this diagram. So here we have a sodium gate, which is a protein channel, and we have a potassium gate, which is also a protein channel. So resting potential, you have sodium on the outside, potassium on the inside, and it corresponds to, number one here, corresponds to negative 65 millivolts on our graph. The cell is going along at resting potential. That keeps happening until some form of stimulation occurs. It could be electrical, it could be chemical, it could be mechanical. But the big thing that happens with stimulation is that it increases sodium permeability. So the cell becomes more permeable to sodium, so a little bit of that sodium, a small amount, starts to leak into the cell. We still have our potassium on the inside, gate still closed, so sodium starts to leak in, and what that causes is the voltage starts to creep up a little bit. So number two is stimulation, the voltage starts to rise slightly. That's going to keep on happening until we reach what's called a threshold level of negative 55 millivolts. And when we hit negative 55 millivolts, that's called the threshold. When we hit negative 55 millivolts, the next event occurs, and that's called depolarization. So at negative 55 millivolts, the sodium gates, which is purple, the sodium gates open. So here we're going to have our drawing. We have our sodium gate open, potassium gate is still closed. We have a big concentration of sodium to the outside. We've opened a passageway for it to travel, and lots of sodium floods into the cell. So we have a big pile of sodium moving in. That's going to cause our voltage, because we've added a whole bunch of positive charge to the inside, to move up very rapidly. And that happens up until about plus 40 millivolts. So that's number three on our diagram, that's depolarization. We dumped a whole bunch of sodium into the neuron. At plus 40, the sodium gates close, and a new set of gates, the potassium gates, open. So now we have closed sodium gate, and we have sodium on the inside where it wasn't before. We also have potassium on the inside where it normally is. This gate is now open, so potassium is going to exit the cell. We have lots of positive charge on the inside at plus 40 millivolts. we lose a lot of positive charge, so the voltage drops back down. That's number 4, and it drops back down until it hits about -75. When we hit -75, the potassium gates close. So now we have 2 gates closed, but we have a problem in that potassium is on the outside and sodium is on the inside. The ions have flipped positions from where they were before. So now it becomes important to talk about this pump here, the sodium-potassium pump. During the part that's called recovery, we have the sodium-potassium pump. What it's going to do is it moves potassium in, and it moves sodium back out. So it's going to act to restore the ion concentrations. I'll just draw another pump here, and what it's going to do is take sodium and move it back out. It's going to take potassium and move it back in, and in doing so it's going to get us back to what we were at resting potential, so that we can fire another signal. So this line goes like this, and that's number 5, and that's our recovery period. We'll talk about how this ties into the whole process of moving signals in class, but this is an introduction so you can see it in advance of class and know what's going on a bit better.